Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we are continuing our study of Chapter 5 on thermodynamic processes and cycles, and we are looking at reheat and regeneration as ways to improve the basic Rankine cycle. The reheat cycle is a fairly straightforward solution to the problem that we've been encountering, right? As we make modifications to increase the thermal efficiency, we end up with quality coming out of the turbine that is just too low. We're going to end up damaging our equipment. And replacing this very expensive equipment is not going to be something that will make your boss happy, I promise you. So how could we avoid this, or at least minimize the risk, right? So there are, different things we could do. We could keep playing with the pressure and temperature, but we could also simply remove the fluid from the turbine earlier, right? Before it gets to that low value of Q2, okay? And reheat the fluid. Just send it back into the boiler or a section of the boiler and reheat it, and then send it back into the turbine to complete the expansion. It's going to work. It will lower the thermal efficiency a bit, but it does protect the equipment. So it's used occasionally just as a protective measure. If you were to follow this, now the numbering system is different than what we had done before. We would have started at 3 before, but here the numbering starts at the pump. So let's just go ahead and start there. As we're looking at this, what we've got is that we have the pump here, and the feed is going to be typically a saturated liquid. We're going to pump it to a higher pressure, so it's going to be a compressed liquid. Now we're going to send it through the boiler. It will come out with a high temperature and high pressure with lots of energy so that it will go into the turbine and turn those blades and produce power. But now then, before it gets to that dangerous region of the saturation curve, right, then we're going to take it out of the turbine and run that same fluid back into the boiler a second pass. That is sometimes called a reboiler, that portion of it. And then we're going to come out of the boiler and come back into the rest of the turbine. So essentially what we've done is we put a wall in our turbine. We could also do this with 2 separate devices, but we're going to add this medium pressure, medium temperature, well, high temperature, but medium pressure fluid back into the turbine, produce more power, and then that will come back through the condenser and again complete our cycle. So all of the analysis is exactly what you've done before. It's just that there are more steps, but you know how to do each one of those steps. So our assumptions are that every heat transfer device is going to be isobaric, because even if it isn't, it really makes very little difference thermodynamically. The boiler and the reheater, we're going to just heat it back to Q equals 1 unless someone tells us otherwise, right? So we can superheat it, but we are at least going to get it to saturated steam. We're going to assume always that the condenser cools things down to saturated liquid. And then we're going to assume that the ideal is reversible and adiabatic pumps and turbines. We can use process efficiencies if we want to know the reality. Our network is going to be the sum for all pieces of the turbine, so the high pressure turbine and the low pressure part of the turbine, and for all pumps. Now in this case we only have 1, but that's our network. And Q for the boiler also happens in 2 stages. We have to count the heat initially going into the feed to the high pressure boiler, but also the part between the high pressure turbine and the low pressure turbine. We need to count all of that. There is another way that we can more closely approach the Carnot or maximum efficiency, and make better use of our resources, right? Improving that second law efficiency. So the way to do that is to basically preheat the fluid going into the boiler. This is called a feedwater heater. So we have the material that's come out of the turbine, and we're going to use our streams to preheat that. Now the feedwater heater that we're adding here, there are two ways of doing it. One is an open feedwater heater where we allow the fluids to mix, and the other is a closed feedwater heater, which is just essentially a heat exchanger. The closed feedwater heater is somewhat simpler because the fluids are not mixing, so I just model them as a heat exchanger. But it's also, in other respects, it's got a little complexity there because we're going to have to add an extra step in our process analysis. The open feedwater heater where the streams mix, the complication with this one is that I can only mix streams if they have the same pressure. So I'm going to have to take hot and cold streams that are not naturally at the same pressure, and I'm going to have to finagle the system to create that same pressure. The open feedwater heater is going to be the less expensive, but it's going to require one extra step of analysis that is different for us. Okay? Both of these are going to require processing multiple streams, and therefore including the material balance will be critical here. This is a system with an open feedwater heater. It's not a great image, sorry, I got it offline. But here we have our material. If we start at the turbine, which is at the top, we bring material into the turbine, but we take some of it all the way through. That would be stream 7 in this diagram. Part of it we're going to slip out early, okay? We don't want to take too much out because reducing the flow rate through the turbine is going to reduce the amount of power ultimately that I can create. But I'm going to use that to help preheat the material going into the boiler, reduce how much heat I have to add at the boiler. So the turbine is going to have one stream in and two streams out. The condenser is fairly normal. The pump is fairly normal. The only difference is they are not operating with the full flow rate, right? Part of the material was taken out earlier. Next, we're going to take that midstream from the turbine and the flow out of our pump and combine those at this intermediate pressure to preheat the material going into the second pump. So we have two pumps and an open feedwater heater. That pump then is going to take it up to the feed conditions for our boiler, and we have completed our cycle. So streams shown here, 3, 4, 5, all are the full amount of the flow. 6 is a small percentage, maybe 10, 15%, something like that we might take out. And 1, 2, and 7 are, if that was 10 or 15%, this would be 85 or 90%, go through streams 7, 1, and 2. This is a diagram of a closed feed water heater. So what you see here again is the material comes out of the boiler, goes into the high pressure turbine. It then leaves that turbine, but there is a split. Some of it's going to go onto the low pressure portion of the turbine and the condenser and the pump one. Some of it is going to go into the closed feed water heater. The first pump is going to send material through, and so therefore I'm going to have a heat balance on the closed feed water heater. I do not need to worry about the pressures being the same for all streams, but streams 4 and 10 must be the same. Streams 8 and 9 must be the same. The material that comes out of stream 3, the split point out of the turbine, is going to go stream 3. It's going to split into 4 and 5. 4 is then going to pass through this closed feed water heater to stream 10, and then through the pump to the high pressure to stream 11, where it will then mix with the material out of pump 1. Both pump 1 and pump 2 are going to have to exit to the same high pressure so that that mixer works. And then we're back to the cycle. In order to do this, the heat exchanger, I think, is not too complicating, but you have two places where you're going to need to do material balances. You don't need to do energy balances on these, only material balances. And this is on your split point, where stream 3 equals streams 4 plus 5, and on your mixing point just before the boiler, where streams 11 and streams 9 mix together to feed the boiler stream 1. So this is a quick overview of what you need to know to modify the Rankine cycle to improve performance, protect equipment, make better use of our resources. We're going to look at another type of power cycle in our next video lesson. Thank you very much for your time.